Okay, in question number 4, we are provided functions g and h as shown. And for the first part, so part A, we are asked to solve when g of x equals 3. And we want to make sure that x is in the domain of g. So first of all, what does it mean if x is in the domain? Remember that this value and this value have to always be greater than 0. So if we see a variable back here, I'm just going to come off to the side, and I'm going to say, okay, I know this has to be greater than 0. So I'm going to subtract 4, subtract 4. So whatever answer I get, I just need to make sure that it is greater than -2, and then I know that I have a correct answer, as long as my algebra matches up. Okay, so I'm going to take 3, I'm going to set it equal to what g of x is, log base 4 of 2x plus 4. Then I'm going to rewrite this in exponential form. Base remains the same. Value on the opposite side of the equal sign goes as the exponent, and we're going to set it equal to whatever was behind, in this case, log base 4, 2x plus 4. Now, 4 cubed means 4 times 4 times 4. 4 times 4 is 16, and then I need 6 groups of 16. So 6 groups of 16. So I have 16, 16, 16, and 16. That's 4 times 16, same as adding 16 twice. So I have 32 and 32. So this is 64 on the left. Subtract 4, 60 equals 2x, divide by 2, divide by 2, 30 equals x. 30 is greater than -2, that means it's part of the domain. Okay, let me just make a little space here, and we're going to go on to the second part, which definitely looks confusing, easier than you think. Okay, so the second part says solve when h of x equals pi over 3. So I'm going to do the same thing I just did for part 1. I'm going to take, in this case, pi of 3, and I'm going to set it equal to, like I took g of x equals 3, and I set it equal to g of x. I'm going to take pi over 3, and I'm going to set it equal to what h of x is. Now, you may be thinking to yourself, what do I do here? So in order to eventually solve for x, what I need to do is I need to get x by itself. So if you remember here, I can write arc sine. That's what this is, right? And so opposite of arc sine is just sine. So I'm going to do sine of pi over 3, and then I'm going to do sine, and then I'm going to write everything that was already here. Now the sine and the arc sine are going to, we don't like the word canceling out, but really what they're going to end up doing is canceling out, right? They're going to disappear every single time, whether it's just cosine and arc cosine. Remember, arc sine is the same as sine with this -1. They will cancel each other out. So what is the sine of pi over 3? Well, first of all, where's pi over 3? In the first quadrant, I have 3 common angles, pi over 6, pi over 4, and pi over 3. So I'm going to do this really quick. 1, 2, 3, 1, 2, 3. Sine is the second number. So square root of 3 over 2 is the sine. And in quadrant 1, where pi over 3 lands, sine, cosine, tangent, and the reciprocals are all positive. So this is equivalent to the square root of 3 over 2. Now how do I get rid of the 6? I'm going to divide this by 6 and divide this by 6. So I personally like to write this horizontally. I have this quantity divided by 6. So stay, change, flip. So square root of 3 over 12, and a great question I often get asked is, can the 3 and can the 12 be reduced? They're not in the same form. They cannot be reduced. This is my final answer. And although I really want to circle this, you want to hesitate from doing that because then it negates all the work. The reader can't score this. They can only score this portion, and if it asks you to show your work, you'd be in trouble. All right, we're going to move on to part B. The first part says to rewrite j of s as an expression, and in that expression we only want to see cosine. So it doesn't matter if cosine lands in the top or the bottom as long as there's just a cosine. All right, I know cosecant could be rewritten as 1 over the sine, and I know that tangent is going to be sine over cosine. Okay, they are going to be reduced or simplified, and so j of x equals 1 over the cosine, and I've done that. I have now rewritten this, and I have only cosine. A common mistake I've seen students make before is they're so programmed now to write this as secant. They are not asking you to write as a secant. They want you to rewrite it with only one cosine involved. Let's move on to the second part of B. This is tricky. Definitely doable, but it is tricky. So in the second part of B, we want to rewrite k of x as an expression in the form 9 raised to the ax plus b, where a and b are constants. So the first thing I'm going to do is I'm going to look at only the top, and I want to rewrite it in the form so that the base is 9. So I can know that 9 squared is equivalent to 81. And then I'm going to look at the bottom, and I want to rewrite the bottom also in the form of 9. So I'm asking myself, like, how can I write 9 as a base and still end up with 3? So as a quick reminder, if I take 4 to the 1/2, I get 2. If I take 9 to the 1/2, I get 3. In fact, if I take 16 to the 1/2, I get 4. Taking these values, taking these values 1, 4, 9, 16, right, and 25, taking those perfect squares and raising it to the 1/2 is the same as taking the square root. So I know that 9 raised to the 1/2 is 3. Okay, now it's going to become a lot easier. So I can now rewrite this as 9, and when you have a power or an exponent raised to another exponent, you multiply. So this is 8x. We're a few steps away from being done now. When you have the same base and you're multiplying, you add the exponent. So this is the same as 9 raised to the 8x plus x. And 8x plus x, well, 8x plus 1x is 9x. So in the numerator, I have 9 raised to the 9x. This is just a coincidence. These happen to be the exact same number. And now we're on to our last step. When you have the same base and you're multiplying, you add the exponents. When you have the same base and you're dividing, you subtract them, and it's always going to be the top subtract the bottom. And there we go. So we now have rewritten this in the form where 9 is the base, and we have an ax plus b. So a is our 9, and b is our negative 1/2, and we can see the work to get that. One says the function m is given, and find all input values in the domain m that yield an output value of 1. Okay. So to do this, what we're going to do is first we are going to set 1 equal to m of x. And then I'm going to divide by the square root of 2. And now I want to remove that sign. So what I want to do is I want to do the arc sign to both sides. So I'm going to do the arc sign on the left and the arc sign on the right. Now another way to write arc sign, just so you know, remember that arc sign is the same as the sign to this negative 1. Okay? So before I write down 1 over the square root of 2, I recognize that that is equivalent to square root of 2, square root of 2, square root of 2 over square root of 4. It's equivalent to the square root of 2 over 2. These two are equivalent. Now what happens over here? These two will wipe out, and that's why we do it. And I'm left with the arc sign of the square root of 2 over 2 is equal to x minus pi over 2. What is the arc sign of the square root of 2 over 2? Okay, well, so for the sign values, arc sign and arc tangent will give you answers that occur in quadrants 1 and 4, where arc cosines would occur in 1 and 2. So I know that arc sign gives us a positive square root of 2 or 2 right here at pi over 4. Okay? And it also gives a positive over here, to keep that in mind, at 3 pi over 4. Okay? Just so we can keep that in mind. All right, so what I'm going to end up doing here is I know the arc sign, because it has to occur in quadrants 1 and 4, will be at pi over 4, and then I have x minus pi over 2. I'm going to add pi over 2 to the opposite side. This is a 4, and now I'm going to do the butterfly method. 2 pi plus 4 pi over 8 equals x. 6 pi over 8 equals x. And I can reduce it, and then I need to write it in the proper general form next. And for sine and cosine, we will always do that plus 2 pi n, where n is any integer. And remember, for the general solutions for tangent, we do plus pi n. Why is that? Because a period length for sine and cosine is 2 pi for the general parent function, but for tangent it's just pi. So again, we're working with sine, and so we'll go plus 2 pi n, where n is any integer. This would be my solution.